Hello everyone, welcome to the channel Exam Ignite. Today I am continuing the series of YouTube videos of electromagnetic theory. In that module 2 is completed. So next we will move on to the module 3, that is part 1. I will be focusing on Poisson's and Laplace equation. In the part 2 you will be studying about the steady magnetic field. So here first I'll start with the derivation of the Poisson's and Laplace equations. Problems you have to work on that. Only the derivation part is concentrated. You will be focusing on that and as well as the uniqueness theorem and also on the applications of the Laplace equation, that is parallel plate derivation, capacitance, coaxial cable and concentric spheres. These are all very important derivations which helps you in scoring. Next, in the part 2, I'll be discussing about the steady magnetic field, which involves Biot-Savart's law, Ampere's circuital law, curl and Stokes theorem, and magnetic flux and magnetic flux density. Starting with the topic, I'll start with the Poisson's and Laplace equation. Derivation, that is from the Gauss law in the point form, we know that nebula d is equal to rho v. Take it as equation 1, where d is a flux density which we have discussed in the module 2 lecture video, and rho v is the volume charge density. Now homogeneous isotope we write as d is equal to epsilon into E. Consider that as equation 2. So from putting the two equation in the equation 1, what do you get? Nebula into E epsilon naught E is equal to rho v, that is the equation 3. From the gradient relationship, we know that electric field is equal to minus nebula v. So on substituting that to that above third equation, what do we get? Nebula epsilon into minus nebula v is equal to rho v. Right now, put the nebula inside and we get as nebula into nebula v in the bracket, and that becomes a nebula square v, that is rho v. So overall nebula square v, that is a Poisson's equation, is equal to minus rho v by epsilon, where rho v is a 0 in the dielectric medium. That becomes nebula square v will be 0. That is our Laplace equation. Here you have to explain the terms in detail and you have to write the considerations and all to elaborate the derivation. Next, we are having three main different coordinate systems where we are using this to check the whether it satisfies the Laplace equation or not. For the Cartesian, it is dou square v by dou x square plus dou square v by dou y square plus dou square v by dou z square. So the cylindrical of coordinate r, phi and z is nebula square v is equal to 1 by r dou by dou r of r dou v by dou r plus 1 by r square v by dou phi square plus dou square v by dou z square. For the spherical with the coordinates r comma theta comma psi, we get nebula square b is equal to 1 by r square rho v by dou r into r square dou v by dou r plus 1 by r square sine theta dou by dou theta of sine theta dou v by dou theta 1 plus 1 by r square sine square theta dou square v by dou phi square. Application of the Laplace equation. First one is to uniformly charged parallel planes of the infinite extent, that is case of a parallel plate capacitor. We will consider two uniformly charged parallel plates, that is M and N, of an infinite extension. It does not have length, separated by a distance of d. Now the electric potential remains same along the x and y, and it varies only along the z axis. So what we can say, dou v by dou x is equal to dou v by dou y, which is 0. Now dou square v by dou x square is equal to dou square v by dou y square, which is also 0. Consider that as equation 1. From the Cartesian form, write down the second equation and consider it as 2. Now put the first equation in the second equation. That two terms become 0. We get only dou square v by dou z square is equal to 0. Now the solution of the differential equation is what? We know V is equal to Az plus B, where A and B are the constants. Apply the boundary conditions, that is potential at a plane M, B V1 and N B V2. V is equal to what? V1 at Z is equal to 0. So equation 3 becomes what? V1 is equal to B. As Z is 0, A term get cancelled. Now plane N is located in Z is equal to D at a distance. So V will be my V2 and Z will be the D length. So equation 3 becomes what? V2 is equal to AD plus B. So on substituting, we know that from the equation 4, V1 is equal to B So AD plus V1. So what will be my A? A is equal to V2 minus V1 divided by D. Substituting all these equations, that A and B, in the equation 3, that is our main equation, substitute the A and B. What do you get? V is equal to V2 minus V1 by D, Z plus V1. Now we have to find for the electric field between the two plates. So electric field is equal to minus nebula V. Substitute the Cartesian form in that. From the equation 1, we can write it as A, X and Y terms are not there. Finally, we get it as E vector is equal to V2 minus V1 by D into AZ cap. Our second application is the capacitance of the coaxial cable. Very important. You have to consider a cylindrical sphere, a hollow cylinder with radius of R, R1 and R2. Let the charges be a positive charges inside the cylinder. Now what will be the nebula square V is 0. 1 by R into, you write on the Cartesian cylindrical coordinate system equation. From here, for the phi and for the z, it terms become 0. We are having only the 1 by R term. So 1 by R into dou by dou R of R, dou V by dou R is 0. Take the R to the RHS, it becomes 0. Now integrate. On integrating, this dou V by dou R gets as rho R into dou V by dou R is equal to constant A. So send the R to the right hand side, it goes to the denominator. You have to integrate now. On integrating, what do we get? We get V is equal to A into 1 by R, that is what? Ln R plus constant B. Now we have to consider the two cases when the small r, that is the resistance, is R1 and V is equal to V0. So V0 will be A into ln R1 plus B. That is my equation 2. At R is equal to R2, what do you get? V is equal to 0. So 0 is equal to A ln R2 plus B. That is my equation 3. Substitute this 3 into, what do you substitute 3 into means substitute the B in the 2. You get V0 is equal to A ln R1 minus A ln R2. V0 is equal to what? A ln R1 by R2. So A is equal to V0 divided by ln of R1 by R2, which is my equation 4. Put this equation 3 and this in 1. So you have to substitute the A and B. What do you get? V is equal to A ln R minus A ln R2. V is equal to A ln of R by R2. That is substituting the 4 in that. As we know the A, we get V is equal to V0 ln of R by R2 divided by R1 by R2. This is my equation 5. We have to find the electric field, which is minus nebula V. This is the equation of the cylindrical coordinate system. So E vector will be minus dou V by dou R into AR cap. And on substituting the value of that, we get it as this 1 ln R minus ln R2. We'll change it to 1 by R minus 0 into AR cap on differentiating. Now minus V0 by R ln of R1 by R2 into AR cap it becomes. Finally, what you have to do is you have to find the electric field due to the infinite line charge. So the infinite line charge, it is we know the equation, it is rho L divided by 2 pi epsilon naught R into AR cap. Compare the 6th and the 7th equation. You will get it as V0 divided by R ln of R2 by R1, which is equal to Q by L divided by 2 pi epsilon naught R. So Q by V0 is equal to, it goes to the numerator, 2 pi epsilon naught RL divided by R by N into R2 by R1. So we need to find the capacitance. Capacitance is, we know, charge by voltage, that is Q by V0. We get the equation as C by L is equal to 2 pi epsilon naught divided by ln of R2 by R1. Our next application is two concentric spheres. We consider two concentric spherical cells of M and N of radii R1 and R2, where R2 is greater 1. We know that by the spherical coordinate system, we know the formula. Now the electric potential remains constant for the theta and phi, but it varies only for the r coordinate. So the theta and phi terms becomes 0. So 1 by r square dou by dou r of r square dou v by dou r is 0. Send the 1 by r square to the RHS, it becomes 0. On integrating, we get r square dv by dr is equal to a, which is constant, consider it as 3. dv by dr is equal to a by r square. On integrating on both the sides, integration of dou v is equal dv is equal to a into integration of dr by r square. We get it as a is equal to minus a by r plus b, where b is our constant. Let the potential of at m be v naught and r is equal to capital R. V naught will be what? Minus A divided by R1 plus B, my fifth equation. The potential at N be 0. So R is equal to capital R2, where it is 0, that is minus A by R2 plus B, where B is equal to what? A by R2. This will be sixth equation. Put this sixth equation in this 5, substitute the B. What you will get? You will get minus A by R1 plus A by R1, which A by R2, which is take the A common, 1 by R2 minus 1 by R1. So A is what? V naught divided by 1 plus R2 minus R1. On substituting both A and B, we get this equation. On solving and simplifying, where our R lies between R2 and R1, you will get the electric field spaces between the two plates is E vector is equal to minus dou V. Now E vector is equal to minus of T by dr into V. Substitute this V here. You will get the final equation as electric field is equal to V naught divided by R square of 1 by R1 minus 1 by R2 AR cap. We know E is equal to Q by 4 pi R square. So capacitance is equal to what? Q by V naught. So that is 4 pi epsilon naught divided by 1 by R1 plus minus 1 by R2. Uniqueness theorem. This is to solve the problems like the boundary values Laplace equation, two different values. We use this theorem. Assume that there is a Laplace equation for V1 and V2. That is, we know the nebula square V1 is 0 and nebula square V2 is 0. To satisfy the boundary condition, equipotential surface, we consider V1 is equal to V2. Let the difference between the two solutions will be Vd. So Vd is V2 minus V1. Apply the Laplace equation to the equation 3. What it becomes? Nebula square Vd is equal to nebula square of V2 minus V1 will be 0. As we know, nebula square V2 minus nebula square V1 is equal to 0. It is my fourth equation. Now consider the divergence theorem. That is volume integral of nebula dot d into dv is equal to surface integral of d vector dot ds. Change it to the vector algebra. From the vector algebra, Vd is Vd into nebula Vd. What do we find is Vd into nebula Vd plus nebula Vd of nebula Vd. So here what happens is this terms become 0 and finally we are left with only this term. In this term we are going to substitute back to our this equation, divergence theorem. So hence we get volume integral of dou Vd into dou Vd whole into dv is equal to volume integration of nebula Vd into nebula Vd into dv is equal to 0. If the solution of the Laplace equation satisfies the boundary condition, and then the solution is unique by whatever method it is obtained. So this completes the part 1 of the module 3. Do subscribe and share with your friends for the module 3 part 2 video. Thank you.